In the previous video, we talked about, in general, how equilibrium concentrations reach some kind of a static point, and we were able to use particle pictures to predict the direction of reaction movement if we were not at equilibrium. Of course, that's impossible in real life because we can't see the particles. And so today we're going to learn how we can use concentration and pressure to develop a strategy for determining, first of all, is a system at equilibrium? And then second of all, if it's not, what's going to happen? So let's go back to this reaction that we had in the previous video. This is HI decomposing to H2 and I2, and it's a reversible reaction. One version of this reaction that was run, you start with all HI, 0.2 moles per liter concentration, and with no H2 and I2. After letting it come to equilibrium, the concentration of HI is 0.16 molar, and the concentrations of H2 and I2 are both 0.02 molar. Then we did the reaction with a different starting point. Here we had no HI initially, but we had 0.3 moles per liter of H2 and I2. After the reaction reached equilibrium, we had 0.48 molar HI and 0.06 molar concentrations of H2 and I2. And then in the third reaction, we started out with 0.10 molar of all three, HI, H2, and I2, and when we reached equilibrium, we had 0.24, 0.03, and 0.03 for the concentrations of HI and H2 and I2, respectively. One way that we might start looking for a way to quantify where we're at equilibrium would be to take a ratio of products over reactants. And when we do that, we find 0.00375, 0.0075, and 0.0025. Now, there's definitely a trend here. When we doubled the initial concentration of HI from experiment 1 to experiment 2, we found that we doubled that ratio. And when from experiment 2 to experiment 3, we cut the initial concentration of HI to a third, we also found that that ratio cut to a third. But those ratios are all different. There doesn't seem to be a single predictor that could allow us to determine if we were at equilibrium or not. Let's see if we can work out a strategy. Say you have a generic reaction where A moles of A react with B moles of B reversibly to produce C moles of C and D moles of D. So the lowercase letters are the coefficients and A, B, C, and D are the reactants and products. Let's assume as a starting point that this is an elementary process in both directions. And if it's at equilibrium, then the forward rate and the reverse rate would have to be equal. Since we're assuming that these are elementary processes, the forward rate is going to be K forward times concentration of A raised to the A power times concentration of B raised to the B power. And the reverse rate is going to be K reverse times concentration of C raised to the C power times concentration of D raised to the D power. But if it's at equilibrium, these are equal to each other, so that means we could say K forward times concentration of A to the A times concentration of B to the B equals K reverse times concentration of C to the C times concentration of D raised to the D power. But this would mean that K forward divided by K reverse, which is just another constant, would be equal to concentration of C to the C, concentration of D to the D, over concentration of A to the A, concentration of B to the B. That constant is what we call the equilibrium constant. And when it's in terms of concentration, we call it Kc. It's important, I think, to get in the habit of using a capital K here. I don't always remember to do that. But we want to distinguish between the rate constant and this equilibrium constant, because this is not the rate constant. Well, now let's test it with our data. If we take the concentration of H2 and I2 and raise them to the 1 power, because their coefficients are 1, and then divide by the concentration of HI squared, because its coefficient is 2, here's what we get. For the first experiment, 0.0016. The second experiment, it's the same thing. For the third experiment, it's the same thing. So regardless of the starting concentrations, this ratio of concentrations of products over concentrations of reactants raised to their coefficients was constant for all three experiments. Now, this is not how this was originally developed. a much more rigorous approach that was based on non-elementary processes and some advanced thermodynamics is how we originally found this. But experimental observation verifies that this works for all equilibrium systems, regardless of if they are elementary processes or not. So we can rely on that. What we've been working with is something called a homogeneous equilibria, and that's where all of the reactants and product species are in the same phase. So all aqueous, or we could also do this if they were all gaseous. If something is not aqueous, then it doesn't really have a concentration. So, or at least its concentration would be constant. So it would not appear in that K expression. Or if something is not a gas, it would also not have a concentration, or its concentration would be essentially constant. So the rule of thumb is you take the products and raise their concentrations to their coefficients and multiply them together, and then divide that by the same thing, only for reactants. This should be a capital A right there, I noticed. There's a pressure version of this that also exists, which is more convenient if your system is mostly gaseous. So it's the same thing, it's the ratios of products raised to their coefficients over reactants raised to their coefficients, but instead of concentrations, we're putting in pressures. Now these are related to each other. Here's how they are. Pressure, we know, is equal to nRT divided by V, which we could rewrite as pressure is equal to N over V times R times T, but N over V is molarity if the volume is in liters, so we could write this as M times R times T. So Kp could be thought of as molarity of C to the C times molarity of D to the D times RT to the C plus D, and then molarity of A to the A times molarity of B to the B times RT to the A plus B. Or we could write that as Kp is equal to concentration of C to the C times concentration of D to the D divided by concentration of A to the A times concentration of B to the B times RT raised to the C plus D minus A plus B. But this term here, that's just Kc. So Kp is equal to Kc times RT to the C plus D minus A plus B. But C plus D is the number of moles of gas in the product side, and A plus B is the number of moles of gas in the reactant side. So what we're doing really is we're raising it to the change in the number of moles of gas in the reaction. So that gives us a conversion factor between Kp and Kc. So let's do an example of a conversion like this. What's the value of Kp for this reaction if Kc is given? So thinking about this, one thing we're going to have to know is what's the change in the number of moles of gas. So the change in number of moles of gas is 2 moles of gas on the product side coming from 1 mole of gas on the reactant side. So that's a 1. So what's Kp? Kp is equal to Kc, which is 4.63 times 10 to the negative third, times R, and we're going to use the chemistry R, 0.0821, and we're kind of ignoring units at this point. These are usually expressed as unitless, and that's times 298 because it's 25 degrees C raised to the 1 power, and that gives us 0.113. So that's the Kp that goes with that Kc for this reaction. Let's talk about generally interpreting equilibrium constant. If K is about 1, then that means the ratio of products to reactants is about 1. And so that means at equilibrium you're going to have about the same amount of reactant as product in concentration or pressure terms. If K is way bigger than 1, that means you're going to have way more product at equilibrium than you do reactant. And conversely, if K is much smaller than 1, that means when you reach equilibrium you're not going to have very much product. It's still mostly going to be reactant. So let's look at 3 particle picture examples. We have 3 choices, 1 over 59, 30 over 30, and 59 over 1. So there are 60 particles in each box. In the first reaction, the product is that orange particle. There aren't very many of them. So the numerator is going to be small and the denominator is going to be big. So that goes with that box. In the second box, green is the product. It's mostly green and there's very little reactant, so the numerator is going to be very big, so that's the Kc that's going to go with that box. In the third box, it looks like it's a pretty equal mixture, so that's the K that's probably going to go with that box. There are some properties of equilibrium constants that allow us to work with them when the equilibrium reactions are expressed in different ways. Let's take a look at one of them. For the reaction that the generic reaction we've been using, written as it is, we see that Kc is the ratio of C to the C, D to the D over A to the A times B to the B concentrations. If we were to reverse that reaction so that the C and D were the reactants and the A and B were the products, well, then A and B would be in the numerator and C and D would be in the denominator, but everything else would stay the same. So the rule of thumb is the K for the reverse of the reaction is the reciprocal of the K for the forward reaction. So if for N2 and 3H2 becoming 2NH3, if we were to reverse this, so 2NH3 we're decomposing into N2 and 3H2, at the same temperature, what would Kc be? Well, it would be 1 over 2.4 times 10 to the negative third, which would end up being 420. So you just take the reciprocal when you flip the reaction around. The next question is, how does the equilibrium constant change if we multiply the coefficients by some constant? So here's our generic reaction again. What if we doubled all the coefficients? What would Kc look like? Well, everything would be the same except for you'd be raising it to twice the original coefficients, which means we'd be squaring the original Kc value. So the rule of thumb is, when you multiply the coefficients by some n, raise the equilibrium constant by that n. Example problem. We saw this equilibrium before. What if we divided all the coefficients by 2? This is a mistake. That should be 3/2. Since we multiplied all the coefficients by 1/2, we should raise the K value by 1/2 as well, which means taking the square root of it. So Kc for that second reaction would be the square root of 2.4 times 10 to the negative third, which ends up being 0.049. What happens if we add some reactions together that are at equilibrium? So let's say we have A becoming B. The K for that reaction would be B to the B divided by A to the A concentrations. Then let's say there was a second reaction where B becomes C. K for that reaction is going to be C to the C divided by B to the B. If we add these together, we would get A becoming C directly. K for that reaction will be C raised to the C divided by A to the A. But that could be rewritten as B to the B over A to the A times C to the C over B to the B. And B to the B would cancel out, and that just gives you that Kc. But this was Kc1, and this was Kc2. So we have this rule called the rule of multiple equilibria that says that the Kc for a sum of reactions is a product of the Kc's for the original reactions. So let's apply some of these identities to a problem here. The question is, what is Kc for this overall reaction if we're given these two reactions? Let's move to a space where there's more room to work and solve this problem. I want to have NO2 on the left-hand side, and I want to have 2 moles of it. So I'm going to take this equilibrium and write it exactly as it's written. 2NO2 gas in equilibrium with 2NO gas and O2 gas, with my Kc being 1.1 times 10 to the negative fifth. I don't want any NO in my product side, the first reaction, and I'm going to flip it around so that's NO, so it will cancel, gas, in equilibrium with 1/2 N2 plus 1/2 O2. These are both gases. Now I have to cancel 2 moles of NO, so I'm going to multiply this through by 2. So that becomes a 2, that 1/2 becomes a 1, and this 1/2 also becomes a 1. When I do that, my Kc, I have to square it. So that's 1 divided by 4.8 times 10 to the minus 10th. And I'm taking the reciprocal because I flipped it around. But then I have to square it. It's 4.3 times 10 to the 18th. So when I add these together, my NO canceled like I planned, and I end up with 2NO2 gas in equilibrium with O2 gas plus another O2 plus N2 gas. And that's the reaction I was looking for. And Kc is going to be 1.1 times 10 to the negative 5th times 4.3 times 10 to the 18th. And that comes out to 4.8 times 10 to the 13th. There's a quantity called reaction quotient. Sometimes it goes by another name. It's also called the mass action expression. And it has the same formulation as K. So for in concentration terms, it looks just like Kc, and in pressure terms, it looks just like Kp. The difference is that K is for these concentrations or pressures when they're at equilibrium. But Q doesn't have to be at equilibrium. At equilibrium, however, Q equals K. So that means if Q isn't K, the reaction is not at equilibrium. And we can also get some clues about what's going to happen to the reaction by looking at how big Q is compared with K. So for example, if Q is bigger than K, what that means is the numerator is too large and or the denominator is too small. So in order to make the numerator smaller and the denominator bigger, we would want to have less product and more reactants, since product's on the top and reactants on the bottom. So this reaction would shift to the left if Q is too big. If Q is too small, then that means we need the numerator to get bigger and the denominator to get smaller. So we would make reactant into product to change that, and that means the reaction would shift towards the right. It would occur in the forward direction. Let's take a look at this with a simple particle example. We have 2 red in equilibrium with 1 blue. And the first question that we have to ask is, what is Kc? There's a little bit of a code here that tells us that 1 sphere represents 1/100th of a mole. We also know that in our equilibrium container here, the volume is 1 liter. So let's evaluate what Kc is by first of all looking at what the expression would be for Kc. Blue is the product, so concentration of blue would be in the numerator. Red is the reactant, so concentration of red would be in the denominator, and it's squared because the coefficient is 2. So in terms of what's in our container right now, we have 0.0300 moles per liter for blue, because there are 3 particles, and 0.0300 moles per liter for red as well, but that's going to be squared. When we do the math here, we get 33.3 as our value for Kc. The next question is A at equilibrium? Well, let's figure out what Q is. Q is going to be 0.0300 moles in a half a liter, because the concentration is going to be increased because the volume has decreased. And then in the denominator, we're going to have still 0.0300 moles over a half liter, and this is going to be squared. When we calculate this, we get 16.7. But remember, K was 33.3, so Q is not equal to K, so this is not at equilibrium. So what direction will the reaction go in A, now that we know it's not in equilibrium? Because Q is less than K, the reaction is going to shift to the right to use up reactant and make the denominator smaller and make product, which will make the numerator bigger. And then the value of Q will rise until it is at K. Next question is B at equilibrium? Let's figure out the mass action expression. Q equals 0.0600, because now we have 6 blue particles in there. Still a half a liter of volume. And in the denominator, we still have 0.0300 moles in that half liter for reds, and that's going to be squared. When we calculate this, it's 33.3, So in fact, it is at equilibrium, and there's not going to be any shift because Q matches Kc. Here's a non-particle picture example. We have a temperature given, a Kp is given for the reaction between a gas and two other gases. And we have partial pressures of all three of the gases. They're placed in a container. And the question is the reaction at equilibrium? And then the follow-up is, if it's not, what direction will the reaction shift to reach equilibrium? Let's go to a place where there's more space to work and answer this problem. To determine if this reaction is at equilibrium or not, we're going to have to compare Q with K. So let's first of all evaluate what would Q be. Let's use Qp because we have pressures here. That's going to be pressure of hydrogen times pressure of bromine divided by the pressure of HBr squared. And all of these go in that expression because they're all three gases. So under the conditions that we have here, the pressure of H2 is 0.010 atmospheres. And for bromine, it's also 0.010. And then the pressure of HBr is 0.20 atmospheres, and that's going to be squared. When we work this out, we get 0.0025. If we look at what K is for this reaction, Kp is something times 10 to the minus ninth, and this is much, much bigger than that, many orders of magnitude bigger. So because Q is greater than K, that means the reaction is going to shift to the left, and we're going to produce more HBr by consuming up some H2 and Br2. Here's another one at some temperature. We have a Kc value here, and we have the reaction given. 2NO is in equilibrium with N2 and O2. They're both gases, and so is NO. And we have some moles of each reactant product, and we know that the volume of the container is 2 liters, and the question is it at equilibrium, and if not, which direction will it shift? So again, let's go to a working space and solve this problem. Just like in the last problem, here we want to, once again, evaluate Q and compare it with K. So we're going to use QC because we have what we need to determine what the concentrations are. It's going to be concentration of N2 times concentration of O2 in the numerator, because those are my two products, divided by the concentration of NO squared. And under our conditions here, that's going to be 0.62 moles in our 2 liters for the N2 and 4 moles in our 2 liters for the O2. And then in the denominator, we have 0.032 moles in our 2 liters. When we calculate this all out, we come out to 2,400. And when we look at the value that we're given for Kc, QC is approximately the same thing as Kc. So that means this is at equilibrium, and we would not expect to see a shift to the left or to the right.